I flipped over and it says permutation. So we're actually starting what a permutation is. And a permutation is an arrangement of a set of objects. So an arrangement in a specific order of a set of objects is called a permutation. So when we want to know how many ways that we can select and organize, order is important, right? A set of objects, then we want to know the number of permutations. So what I mean by order is, just quickly, if I took my numbers, like let's just take 2 digits, 2 and a 4. There are 2 different ways I can order those numbers to create a 2-digit number, right? I could call the number 24 or the number 42. This is what we call 2 permutations. Permutations is a fancy math term for orders of the digits 2 and 4. So order is important. When you pick a PIN code, let's say you remember your PIN code has 3 digits, and you can remember the 3 digits, but you can't remember the order. The order is important. The order is a permutation. So the order is the exact order of the digits or the letters or the people. If I said, Eileen and Joanne, go to the office, Aaron wants to talk to you, it doesn't, like, that's just a combination. That's just 2 ladies going to the office. The order doesn't necessarily matter. So there are lots of situations where order doesn't matter. In PIN codes and passwords, for sure, order matters. Right? So let's talk about what happens when order matters. Use a graphic organizer to determine the ways I can arrange the letters of the word car and verify your answer with fundamental counting principle. Okay, how many letters do I have? 3, right? It's going to be like that 5, 6, 7. There's 6 different ways then, right? So graphic organizer would be, well, it could be car. It could be, I could flip the A and the R. And it doesn't matter the order you do them in. I just find there's usually a logical way for me to do them. So if I start with a C, I can flip the A and the R. If I start with the A, I flip the R and the C, right? If I start with the R, I flip the A and the C, and that gives me all of my possible permutations. So I'm actually going to use that word now. 6 different permutations. Now, this is different than the fundamental counting principle when we were just like doing how many colors of t-shirts, how many colors of pants, because there, it wasn't really a permutation. It was just how many different combinations are there. It didn't matter if she put the t-shirt on first or the pants on first. We were just, so it's similar to the FCP, but we're using the FCP principles in a slightly different way. Now here, verify your answer with the FCP. So I've got 3 different letters I can use, right? I've got the first letter, the second letter, and this is the space, the third letter. Just like we did before, I have a choice of 3, 2, 1. So 6 different ways. So what the fundamental count or the permutation is, it's when you're selecting objects from the same pile of objects, right? I'm selecting all letters of the word car. I'm not selecting a t-shirt from one pile, a pair of pants from another, or a sandwich from this bin and a drink from this bin. A permutation arises when you're selecting from the same pile of things, like the same group of students that we had on that number 10, or the letters from the same word. That's what a permutation is. Okay? Use the fundamental counting principle, so this system, to calculate the number of 4-digit numbers that could be created using the digits 3, 5, 7, 8 without reusing any of the digits. So this is the term I was looking at before. I couldn't see that without reusing expressions, so that allowed me to use the numbers. This means once I've used a letter, I can't reuse it. Another way you'll see this phrase being given to you is without repetition. Sometimes you'll see that, and that means the same thing. Okay, I have 4 slots, right? For my 4 digits. How many digits do I have to choose from first, Abdullahi? 4, okay. So one of the digits is used up, I can't use it again. Then I get a choice of 3, then 2, then 1. See the patterning that develops when I'm selecting from the same pile? 3, 2, 1, 4, 3, 2, 1. So when that happens, when you get a question where you're pulling things from the same pile and they're reducing by 1, you get what's called, you get a factorial. When you multiply numbers, and the sequence is creating by taking 1 less each time, that is called a factorial. So this is a factorial. And let's just read down here. The patterns that develop when we use FCP with permutations, in the first example we got a 3 times 2 times 1, and then 4 times 3 times 2 times 1. When we have this pattern, whatever one number we start with, if we just call it n, then the next number is 1 less than n, and then the next number after that would be 2 less than n, then 3 less than n, can be represented by a special type of notation. It's called factorial notation. And what happens is if we know that when we start with whatever n is, and our multiplication product just keeps going down all the way to 1, I could express 4 times 3 times 2 times 1 as just 4 factorial, okay? And 4 factorial is 24. And the reason I say this is you might get a question that's 15 factorial. Well, you want a quick way to enter it into your calculator, so you're not going to go 15 times 14 times 13. It's on your calculator somewhere, so you have to find that first. And it's just a little, I got to even look for mine. I don't know this calculator that well. Okay, so if you find, you might have just the exclamation mark, but chances are you're going to have, like I do, I have n exclamation right here. So I would do 4, second row, like that, and you get your exclamation mark, and it'll give you 24, okay? It's probably going to be close to the other buttons you'll be using. You'll be using NCR and NPR soon as well. So if you look for that row, they're probably all going to be grouped together.
So you just put it on 4?
Well, no, I went 4. And see, mine's on my second row, so I have to use the second function. You get the exclamation. Okay? I can look at your calculator behind. So this type of notation is very useful, especially when we have huge numbers. So what we're going to do right now is we're going to just get used to the factorial button. Everyone find it. If you don't find it, let me know. Abdullahi? Did you find it? Yeah. Yeah?
Yes.
Do you know where yours is, Eduardo? Yours is hard.
No.
Everyone got theirs? Your buttons? So you're just doing that, maybe? You know what that is, right? So this will become important for us to use in later permutation problems. So if everyone's got theirs, this is just really a matter of, now 9 factorial is going to be a big number, right? What will happen is you'll probably start to memorize or just know from memorization the easy ones like 4, 5, 6 factorial, probably. So everyone should have got that for 9 factorial. This is 5 factorial times 3 factorial. Right, which should be 720. What's 7 factorial subtract 4 factorial? Yeah, 5,016. It said without a calculator do the others, but I'm just curious to see. if you could do, can you do 9 factorial over 4 factorial without a calculator? How do you do that?
Yeah.
If you know how this works, right? Like that one you probably could do with your calculator and get away with it. I wouldn't know. This one you could do with your calculator, even though I said not to, get away with it. This one you won't be able to use your calculator because your calculator doesn't hold numbers that big. So you have to have a process. They usually slip one of those on the exam, something like this. So what I heard the guys say, I heard Eduardo and John say, well, I can simplify this easily. If I think of 9, what does 9 factorial mean? Well, it means 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? And 4 factorial means 4 times 3 times 2 times 1. Agreed?
Cancel those out.
Yeah, so they just cancel out. So this will fit in my calculator. This is something you would have to, I mean, it says without a calculator, so let's actually see if we could do it without a calculator. That would be 30. I've got what, 72 times 30 times 7, I guess. I am going to use a calculator, by the way. I'll erase this. So 72 times 30 times 7, just so I don't make mistakes, 15,120. So that's the process. Now I could actually make this a little shorter, which is probably what you guys did. I could think of it as this. This might be a little more efficient, so I'd have enough room to show my work. When I start streaming out my 9 times 7, now I started with the 9, not because it was on top. I started with the 9 because it was bigger. There's more numbers in 9 factorial than 4 factorial, right? So start with the one that has the most numbers in it. So 9 times 7 times 6 times 5 times, okay, if I just stop here, couldn't I represent 4, 3, 2, 1 as just 4 factorial? Right? Because that's what that is, right? 4, 3, 2, 1. And if I stop there, I could just leave my bottom as a 4 factorial, kind of save me some steps, and I still end up with the same answer, right? 15,120. Oh, thank you. That's why you guys were looking at me all funny. So you don't have to list them all out if you don't want to. You could stop at your lowest factorial. You can cancel factorials out as long as they're the same factorial. So this one could kind of do the same process maybe. I can go 8 times 7, 6, 5, 4, 3. I'll stop at 3 factorial because that's what I have on the bottom. Okay, so the 3 factorials cancel out. What is 2 factorial? 2 factorial is just 2, right? So I could have just recorded that as a 2. And I can cancel one of those out. So then I have 56 times 30 times 2 times 70. No. 6 times 5 times 2 times 56. 3360. That's how we work with factorials. This one, I don't think my calculator would even hold that. Even I know it cancels out. Let's see, I might be wrong. I don't think it, I think I'll get an error, right? Yeah, you get an error. So you have to have a process, right? This one actually is quite easy. 102 is the bigger number, right? So I'm going to start there. 102, then I have 101. Then I have 100 where I'm going to stop now, because that will allow me to cancel out my 100 factorial. So I really have just 102 times 101, right? So why we're learning this, we're actually just learning the math that goes along with this unit, with this type of math. We're going to have to learn to deal with factorials. They're going to happen a lot, just because we're dealing with choices of things, right, and ways to do things. So quite often we're going to have patterning develops. So let's see again. Determine the number of ways, the number of permutations, that you can arrange the letters in each word. Now we're assuming, again, it's like kindergarten. Kindergarten teacher gave you 5 letters on your little table. So that means you just have your letter S, your letter P, your letter I, and you can arrange them around. You can't reuse the letters, right? Once you've put your little letter on your little magnetic board, you can't reuse it. So I have 5 letters, correct? What's going to happen here? I have 5 little slots on my little board on my table. I have a choice of 5. Then I have 4, 3, 2, 1, or you could have just recognized right away. Okay, I have to use all the letters up, so that will be 5 factorial. 120. What about this one? 1, 2, 3, 4, 5, 6, 7, 8. What's the short way to do that? 8 factorial, right? Or I could do my 8 slashes. So 8 factorial. 40,320. It's amazing, right? How quickly the numbers start to climb. Okay, I think I'm going to, I'll just assign a couple of questions for you. I'm going to stop there, okay? I'm going to stop there. And I'm going to assign number 1. Now you can look, again, if you look on page 276, there's lots more reading if you want to do. There's a bunch of examples here on page 277, similar to what I've done. So I bet some of you know what 3 factorial is from memory already. 6. Do you know what 5 factorial is from memory? Yeah? Good. 7 minus 4. What's 7 minus 4? 3 factorial is 6. This one you might, I think we did that one. I think that was the exact one we did. Yeah. Could you do this one in your head? 10 times 9. The 8s cancel. How about this one in your head? 20 times 19. So what's 19 times 2? 38 times 10, add a 0, 380. Yeah. Okay. Let's just try one of these. We haven't done one like this before. Let's just see where your brains go with this. I'm not going to assign one like this for homework, finding n, solving for n. This is solving for n. Solve for n. So don't look at the answer. What does this mean? N plus 1 factorial equals 2n factorial. How would you solve for n? What does it mean to solve for n? What do we usually have to do when we solve for n or solve for x? By the way, all our x's are going to be called n's now because they stand for a number. What do we usually do when I tell you to solve for x? Isolate the x, right? So we have x's or n's on both sides of the equation, and we have factorials. So I'm going to let you in on this one little secret. In order to truly solve a factorial equation, you have to get rid of the factorials. You have to end up canceling them out. Okay, because they actually represent a whole stream of numbers after that. So the quickest way, if you can get rid of your factorials and then just treat it like a normal algebra question. So, I mean, you could look to the side, but I think what I'd start with, again, remember how we were canceling out factorials here? Start with the largest number. So what number would be larger, n or n plus 1? You don't know what n is, but what would represent a bigger quantity, n or n plus 1, right? So start with the bigger number and start kind of streaming it out. So the first term would be n plus 1. Then what term would be after n plus 1? You're going down by 1 every time, right? So it'd be n, which is what I have on the right-hand side. So I'm going to stop there. See how that I did that? Divide out n factorial on both sides. There, you got rid of your factorials. Just like you did up here. It's the same process. Start with the bigger one, stream him out, till you end up with the same factorial that you have on the other side or below. Okay, I got rid of my factorials. Now it becomes just a simple algebra equation. So n is 3. Right? I can't do algebra late in the day, you guys. Notice that. Okay, don't look at the answer. Let's cover it up. Let's try that same process here for this last one. Find n. You've got 3 factorial, n factorial. Don't worry about the numerical factorials. They're easy because they actually represent a number, so they're fine. They'll cancel themselves out later. I've got an n on top and n minus 1 on the bottom. Which represents the bigger quantity, n or n take away 1, n minus 1? N is bigger, right? So start streaming him out. You could even call this 6 if you wanted, right? You know what that is. It's 6. Okay, so n, and then right after n would be the n minus 1, which I'm going to stop because that's exactly what I need to cancel. Okay, so now I have my n minus 1 factorials will cancel out. As long as I can cancel my factorials out, I'm great. So I have 6n equals 30. N is 5. Okay? So as soon as you see that exclamation mark, whatever number they give you to start with, you start with, and you just keep going down one less. Take one away, one away. So let's just try a couple of these. If I started with 70 factorial, and I told you to expand, what would you start with? 70 times 69 times 68, right? 12 factorial, 12 times 11 times 10. Okay. If I start with n, well, I don't know what n is, so I can only do this in theory. Okay, what did I do here? I subtracted 1 from 12, so I start with n. And then n subtract 1 would just be shown as that, right? N subtract 1. Okay, what's my next one going to be? N minus 1 minus another one, n minus 2. And then if you don't know when you want to stop, like you can stop anywhere, but wherever you stop, you just say, okay, it keeps going and going and going. What if I started with this? What if I started with n plus 5? It's going to take a few steps to get to n, right? My first, whatever you're given, that's what you start with. Okay, what's my next term? N plus 4. Right? And then n plus 3, n plus 2, n plus 1. Okay, finally I'm at n. I can stop here if I want. I can stop anywhere, but let's say I want to keep going. Then I would go, yeah, except I would do that and just stop anywhere. Okay? So that's the theory behind it. It's easy to work with real numbers. The theory is just keep subtracting 1. Okay, so I'm going to assign for you, find each of the following values. I'm going to say finish up. I think most of you finished up that previous one. So on page 277, I'm just going to get you to do one, I think just number 1. No, let's see if you can do, try 1 to 3. Okay, so number 1 is just straight numbers. 2 and 3 are just simplifying. To be honest, I'm not sure about number 2. I'm just going to put, maybe we'll look at that one right now. You're not solving anything. 4 and 5 are solving. 3 are just simplifying to see what you can. To be honest, guys, I don't know what they want you to do in number 2. What would happen? You'd have n plus 2, n plus 1, n, right? Okay, is that simplifying? That's making things bigger, right? Okay, so could we make this,
Wouldn't it be n plus 1 squared, n plus 2 and n plus 1 squared?
is there any way to make this smaller?
Make it a trinomial?
What if I went this way? How about this? Isn't that what that means? Kind of silly, right? Because this, if I said to expand it, it would be this, right? So you could just call it n plus 2 factorial, right? Simplify, make it, I don't know, it's kind of a silly question. See what you can do with this one? Now, if you want to go on, of course go on, but these are solving, and that's what we were just doing now. I don't know if you fill up to it if you have the time, but try and get number 1 done for sure. Just number 1, just playing around with factorial. I would challenge you, as much as you can, try and reduce as much as you can without a calculator. Just pick your calculator up on the last step. Like, don't just punch this in. Try and reduce it as much as you can, just to play with the factorials a little bit.